Hello friends, welcome to my lecture on basic concepts of probability. Modern probability theory is based on the axiomatic definition of probability. We define a probability model and state the axioms which any reasonable definition of probability must satisfy. Let us consider a random experiment with a number of possible outcomes. The number of possible outcomes is either finite or infinite. Let n denote the number of possible outcomes. The set of all possible outcomes of a random experiment is called the sample space of the experiment. We shall denote it by S. Each possible outcome is a member of S and is called a simple event. Thus the sample space is the set of all simple events. Simple events are also called sample points or elementary events, etc. In the sex classification of a family having two children, one sample space could be defined as S1 equal to the set of elements 0, 1, 2, that is by the number of girls in the family, while the other could be by the sex of the children according to their order of birth. We may write it as S2 equal to the set consisting BB, BG, GB, GG, where B stands for boy and G for the girl. Clearly, S2 gives more information than that by S1. Although both are valid definitions of sample space, empirical results show that the assignment of equal probabilities is appropriate in S2 and not in S1. Suppose customers arrive in a random fashion during a time interval of t units to be served at a counter, then the sample space consists of 0, 1, 2 and so on. Each simple event represents the number of customers arriving in the interval of t units. Though in practice there is a finite upper bound on the number of customers arriving in a specified time interval, it is convenient to write the sample space such that it has an infinite number of points. A compound event or simply event is a collection of simple events. Thus, an event is a subset of the sample space S. We say that an event A occurs or A happens if any one of the simple events constituting A occurs or happens. Suppose that 100 people in a region are classified not only as potential buyers and non-buyers of a particular brand of soap, but also as males or females. Then a sample point may be characterized by 4 integers MB, FB, MN, FN, giving in order the number of male and female buyers, male and female non-buyers. Here MB plus FB plus MN plus FN is equal to 100 and sample point gives a possible combination. The event relatively more females buy than do the males is the collection of those sample points in which FB over FN is greater than MB over MN. FB over Fn gives the relative frequency of the female buyers. So, FB over Fn greater than MB over Mn. The simple event 772 17 4 is one such point, because here the value of FB equal to 72, Fn equal to 4, Mn equal to 17 and Mb equal to 7. So, you can see that Fb over Fn is equal to 72 by 4 is equal to 18, while Mb over Mn is equal to 7 by Mb over Mn. Okay. Mb is equal to 7 by Mn, Mn is equal to 17. So, clearly 18 is greater than 7 by 17, that is Fb over Fn is greater than Mb over Mn. Okay. So, 772 17 4 is a one such sample point. Now, the event that has no simple events is called the null event, okay, and is denoted by pi. It is also called impossible event. The event A that corresponds to the complement of the set A subset of S is called the complementary event of A, and so in particular if S denotes the sample space, then S complement is equal to phi. Now, the collection of simple events that are common to both A and B is called the intersection of A and B. N is denoted by A intersection B, or B also denoted by AB. If the event AB occurs, it means that both A and B occur simultaneously. Two events A and B are called mutually exclusive if A intersection B is equal to phi. This means that A and B cannot occur simultaneously. Okay, suppose you toss a coin, okay, then if the event A is if A is the event that the head appears and B is the event that the tail appears, then the event A and B are mutually exclusive. When you toss the coin, either head will come or tail will come. If head comes, tail cannot come. If tail comes, head cannot come. So, the two events A and B are mutually exclusive. So, A and B cannot occur simultaneously. The occurrence of one of the events A and B precludes the occurrence of the other at the same time. Consider the sample space of all executives in a company. The event A is the event that those executives who live in their own homes. Okay, A is the event that those executives who live in their own homes. B is the event of those executives who live in rented homes, and C denotes the event that those executives whose living space is at most 5 kilometers from office. Okay. Then A intersection B. Okay. A is the event that those executives who live there in their own homes, and B is the event those executives who live in rented homes. So, A intersection B is equal to phi, but A intersection C may not be phi, because A is the event that those executives who live in their own homes, and C is the event those executives whose living space is at most 5 kilometers from office. So, there may be some executives whose living space is at most 5 kilometers from office, and they live in their own homes. Okay. So, AC may not be equal to phi. Now, let us consider the union of two events. Let A and B be any two events. If either A or B or both occur, we say that A union B occurs, and we denote it by A union B. Suppose the occurrence of an event A implies the occurrence of another event B, then we say that A is subset of B. Now, let us define a sigma field. Let S be the sample space associated with a random experiment E, then a sigma field is a non-empty class B of subsets of S that is closed under the formation of countable unions and complementations. That is the sigma that is the set B, set class B satisfies the following conditions. If A1, A2, A3, An and so on are the sets belonging to the class B, then their countable union I equal to 1 to infinity Ai also belongs to B, and if A belongs to B, then its complement A complement also belongs to B. Now, from these definition of sigma field, we can derive the basic properties of sigma field. If B is a sigma field, then following properties hold. Okay, phi and S belong to B. So, let us first show the part A of the lemma. We have to show that phi S belong to B. So, from the condition 2, from this condition, okay, if A belongs to B, then A complement belongs to B. Okay. So, since B is a non-empty set, okay, non-empty class, okay, so there must be some set at least there in B. So, let us say the set is A. So, if A belongs to B, then its complement also belongs to B. So, A belongs to B, A complement belongs to B implies that A union A dash belongs to B. Okay. A union A dash belongs to B, and A union A dash is S. Okay. So, this implies that S belongs to B. Okay. Now, if S belongs to B, then S complement also belongs to B. Okay. If S belongs to B, then S complement also belongs to B. S complement means that is phi belongs to B, because S is the whole space. Okay. Now, A1, A2, An belongs to B implies that intersection I equal to 1 to infinity Ai belongs to B. That means B is closed under the formation of countable intersections. Okay. So, this we can prove as A1, A2, and so on A n belongs to B implies that their complements belong to B. Okay. Now, B is closed under the formation of countable unions. So, union I equal to 1 to infinity A I complement belongs to B, okay, by this property. Now, this implies that by second property, this that if A belongs to B, A complement belongs to B. So, union A I equal to 1 to infinity complement, okay, complement of this belongs to B. By De Morgan's law, union A I dash dash is equal to intersection A I dash dash I equal to 1 to infinity. Okay. Now, A complement is A. Okay. So, this is intersection I equal to 1 to infinity A I okay, belongs to B. Okay. So, that is to say, since intersection A I complement is equal to intersection A I equal to 1 to infinity, okay, it follows that B is closed under the formation of countable intersections. Okay. B is closed under the formation of countable intersections. Now, if A B belong to B, then A minus B belongs to B. Okay. So, A comma B belongs to B implies that A comma B dash belong to B. Okay. And A comma B dash belongs to B means by this property, that is the class B is closed under the formation of countable intersections. From here we can say that A intersection B dash belong to B. Okay. A intersection B dash is A minus B, or now here you may say that this is countable intersection. How we can say about finite intersection? We can take say A1, A2, A3 and so on, A n belong to B. So, you can take say finite number of them and rest you can take as S. Okay. B is also closed under finite intersections. We can take A1, A2 and so on A n finite number of them, rest A n plus 1 as we can take as S, A n plus 2 we can take as and so on. Then intersection A1 intersection A2 intersection A n intersection S and so on. This will be equal to A1 intersection A2 intersection A n. So, B is also closed under the formation of finite intersections. Okay. So, using this property we can say that when A and B belong to S belong to B, when A and B belong to B, then by second condition A and B dash belong to B, and so A intersection B dash belong to B, but A intersection B dash is equal to A minus B. We can see from here, suppose this is our A, this is B. Okay. Then this is so A intersection B dash. Okay. B dash is this complement of B. Okay. This is B dash, and clearly B dash intersection B dash intersection A intersection B dash is this which is nothing but A minus B. Okay. So, A intersection B dash is equal to A minus B. Okay, so this is how we prove this properties of the sigma field. Now let us go to definition of probability. Suppose we have a sample space S. If S is discrete, all subsets correspond to events, and conversely, and if S is non-discrete, only special subsets called measurable correspond to events. To each event A in the class C of events. So let us consider a class C of events. C is actually sigma field here, the sigma field which we have defined just now, that we are taking as C here. So C is the sigma field. So to each event A in the class C of events, B associate a real number P A. Okay. So you take any event belonging to the class C, associate a real number P A with that, then P will be called a probability function, and P A the probability of the event A if the following axioms are satisfied. First axiom is that for every event A in the class C, we must have P A greater than or equal to 0. Okay. So the second one is for the sure or certain event S. Okay, S is the whole space, so it is sure to happen. So for the sure or certain event S in the class C, P S must be equal to 1. For any number of mutually exclusive events A1, A2 and so on in the class C, P A1 union A2 and so on is equal to P A1 plus P A2 and so on. In particular, for two mutually exclusive events A1, A2, P A1 union A2 is equal to P A1 plus P A2. So we will say that P is the probability function provided these conditions are satisfied. Now let us look at some important theorems on probability. If A1 and A2 are any two events belonging to the class C of events and A1 is subset of A2, then PA1 is less than or equal to PA2. So let us see, we by Venn diagram we can say this is say A1 and this is say A2. Okay. So A1 is contained in A2. Okay. A1 is contained in A2. So we can say that A2 is equal to A1 plus A2 minus A1, or you can put union here. Okay. A2 equal to A1 union A2 minus A1. Okay. Moreover that A1 and A2 minus A1 are mutually exclusive because their intersection is phi. Okay. Where A1 intersection A2 minus A1 is equal to phi. So probability of A2 will be equal to probability of A1 union A2 minus A1. Okay. Since A1 intersection A2 minus A1 is phi, we have PA1 plus PA2 minus A1. Okay. Let us go to the this condition, axiom 3, PA1 union A2 equal to PA1 plus PA2 if A1 intersection A2 is phi. Okay. So here, and you see that A1 A2 are events, so A2 minus A1 is also an event, okay, belonging to the class C, and therefore PA2 minus A1 will be greater than or equal to 0. Okay. So PA2 is greater than or equal to PA1 because PA2 minus A1 is greater than or equal to 0. So if A1 is subset of A2, then PA1 is less than or equal to PA2. So we can say that the probability function is monotone. Okay. The probability function is monotone. Okay. It satisfies the monotone property. Now for every event A, 0 is less than or equal to PA, less than or equal to PS. Okay. Since A is subset of S, you take any event A belonging to the class C of events, then A is subset of S. So PA is less than or equal to PS. Okay. And PS is equal to 1. Okay. This we have already assumed, PS equal to 1 in the axiom 2. So you take any event A subset of S, then P A is subset less than or equal to P S, and therefore, 0 is less than or equal to P A less than or equal to 1, okay, because you take any event A belonging to the class C of events, P A is greater than or equal to 0, okay. So, 0 is less than or equal to P A less than or equal to 1. Now, probability of phi is equal to 0, okay. So, let us prove this. Let A be any event belonging to the class C, okay. Then A union phi equal to A, okay. Since A and phi are mutually exclusive, P A intersection P A union phi, okay, is equal to P A, okay. P A union phi is P A plus P phi equal to P A. This is because A intersection phi equal to phi, okay, they are mutually exclusive. So, then this implies that P phi is equal to 0, because we can cancel P A both sides, P A is lying between 0 and 1. So, we can cancel, and therefore, P phi equal to 0. Now, let us say prove A P A dash equal to 1 minus P A. So, we know that A union A dash equal to S, okay. Then P A union A dash equal to P S equal to 1, okay. Since A intersection A dash equal to phi, A and A dash are mutually exclusive. So, P A plus P A dash we shall get, okay. P A union A dash will give us P A plus P A dash, this is equal to 1, this implies that P A dash is equal to 1 minus P A. So, probability of the complement of A is equal to 1 minus P A. Now, let us come to if A is equal to A 1 union A 2 and so on A n, where A 1 A 2 A n are mutually exclusive events, then P A equal to P A 1 plus P A 2 plus P A n. In particular, if A is equal to S, the sample space, then P A 1 plus P A 2 and so on P A n is equal to 1, okay. So, we have this axiom here, P A 1 union A 2 equal to P A 1 plus P A 2, okay. So, in particular for in case of two mutually exclusive events, P A union A 2 equal to P A 1 plus P A 2, this we can by mathematical induction, from here we can say that P A 1 union A 2 and so on union A n equal to P A 1 plus P A 2 and so on P n. If S A is equal to S, then P S will be equal to P A 1 plus P A 2 and so on P A n. So, P S equal to 1, therefore, P A 1 plus P A 2 and so on P A n equal to 1. Now, here how we get, in particular for two mutually exclusive events, this gives us P A 1 plus P A 2, okay. So, this can be shown once you have P phi equal to 0, okay. So, we can take after A 1, A 2, A 3, A 4, A 5, A 6 all we can take as phi, then P A 1 union A 2 union phi and so on we shall will give us P A 1 union A 2, and P phi equal to 0. So, we will get P A 1 plus P A 2. So, this comes from that we can take A 3, A 4, A 5, A 6 all as phi, and then P A 1 union A 2 union phi union phi union phi gives P A 1 union A 2, and we get here P A 1 plus P A 2 because of the fact that P phi equal to 0. So, if A and B are any two events, then P A union B equal to P A plus P B minus P A intersection B, okay. So, let us prove this. We have suppose we have, this is our set A, this is another set B, okay. Then A union B can be written as A minus B, this is A minus B, A minus B plus B, okay. So, the A minus B union B, okay. So, probability of A union B equal to probability of A minus B plus probability of B, because A minus B intersection B is equal to phi, because A minus B intersection B is equal to phi. Okay. So, now A minus B is A is equal to A minus B union A intersection B. This is A intersection B. This is A intersection B. So, A equal to A minus B union A intersection B, and therefore, P A equal to P A minus B plus P A intersection B, because A minus B and A intersection B are mutually exclusive. So, this gives us P A minus B equal to P A minus P A intersection B. So, this is equal to P A minus P A intersection B plus P B. Okay. So, P A and B equal to P A plus P B minus P A intersection B. This is also called the addition theorem of probability. Addition theorem of probability. Okay. More generally, if A1, A2, A3 are any 3 events, then P A1 union A2 union A3 is equal to P A1 plus P A2 plus P A3 minus P A1 intersection A2 minus P A2 intersection A3 minus P A3 intersection A1 plus P A1 intersection A2 intersection A3. Let us prove this result, because we shall need it later on. So, we have P A1 union A2 union A3. Okay. We can use the result for 2 events. So, let us consider A2 union A3 as B. Let B be equal to A2 union A3. So, then we will have P A1 union B. We have already proved that P A union B is P A plus P B minus P intersection B. So, let us apply that result. So, we have P A1 plus P B minus P A1 intersection B. A1 is equal to B is equal to A2 union A3. So, P A1 plus P A2 union A3 we have, and here we will have P A1 intersection A2 union A3. Okay. Now, again by this result P A union B equal to P A plus P B minus P intersection B, we can write P A1, this is P A2 plus P A3 minus P A2 intersection A3, and here this will be equal to A1 intersection A2 union A3 will be A1 intersection A2 using the property of set theory union A1 intersection A3. Okay. So, this will be equal to P A1 plus P A2 plus P A3 minus P A2 intersection A3. Now, we have one event here, one event here. Okay. So, P A1 intersection A2 plus P A1 intersection A3 minus P A1 intersection A2 intersection A1 intersection A3. Okay. So, this gives us P A1 plus P A2 plus P A3 minus P A2 intersection A3 minus P A1 intersection A2 minus P A1 intersection A3 A1 intersection A3. Now, A1 intersection A2 intersection A1 intersection A3 is A1 intersection A2 intersection A3. Okay. So, this is how we prove the result in case of 3 events. Okay. So, generalization to n events can be done similarly. Now, for any events A and B, P A equal to P A intersection B, P A intersection B dash. Okay. So, let us prove this. We can say A is equal to A intersection S. Okay. S is the sample space. okay, and this I can write as A intersection B union B dash, okay. B is any other event. So, B union B dash is equal to S. Now, this is equal to A intersection B union A intersection B dash, okay, A intersection B dash. Now, A intersection B intersection A intersection B dash equal to phi, okay. A intersection B intersection A intersection B dash is equal to A intersection B intersection B dash. B intersection B dash is phi. So, we have A intersection phi. So, this is equal to phi, and therefore, probability of A is equal to probability of A intersection B plus probability of A intersection B dash. Okay. Now, if an event A must result in the occurrence of one of the mutually exclusive events A1, A2, A3 and so on An. Okay. If an event A must result in the occurrence of one of the mutually exclusive events A1, A1, A2, A3 and so on, then we shall have A equal to A intersection A1, A2, A3 and so on. So, we can say A intersection union AI I equal to 1 to n. Okay. If we take the intersection of A with I equal to 1 to n union AI, then it will be equal to A. So, this will be equal to A intersection A1 union A intersection A2 union A intersection An. Okay. If an event A must result in the occurrence of one of the mutually exclusive events A1, A2, An are mutually exclusive, means AI intersection Aj equal to phi whenever I is not equal to j and Ij vary from 1 to n. Okay. So, this gives you Pa equal to, now A1 intersection A2, A1 intersection A intersection A1, A intersection A2, A intersection An are also mutually exclusive because their intersection is phi. So, probability of A intersection A1 plus probability of A intersection A2 and so on probability of A intersection An, because they are mutually exclusive. Now, let us take some exercises. So, we are given a random experiment where A and B are any two events. So, probability of A is equal to half, probability of B equal to 1 by 3 and we are given that probability of A intersection B is 1 by 4. We have to compute the probability of A complement intersection B complement. Now, probability of A complement intersection B complement is equal to probability of A union B complement. A union B complement is A complement intersection B complement, and probability of A dash, we know probability of A dash is 1 minus probability of A. So, this is 1 minus probability of A union B. Okay. Now, probability of A union B, we know probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B by addition theorem of probability. So, Pa equal to half, Pb equal to 1 by 3 and Pa intersection B is 1 by 4. So, this is how much it is? This will be 12. So, this is 6 here and here we have 4 and here we have 3. Okay. So, 6, 4, 3 and we shall have it 7 by 12. Okay. So, 1 minus 7 by 12 gives you 5 by 12. So, Pa dash intersection B dash is 5 by 12. Now, probability of A dash intersection B. Okay. So, let us see, we have A here, this is A, this is B. Okay. So, A dash is this one, oh sorry, A dash is this is A dash. Okay. This is A dash. So, A dash intersection B will be B minus A. Okay. So, this is probability of B minus A. Okay. Probability of B minus A we have to find. Okay. So, from B we have to subtract A intersection B, this is A intersection B. Okay. So, this is equal to probability of B minus probability of A intersection B, and probability of B is 1 by 3 and this is 1 by 4. So, we get 1 by 12. Okay. So, now let us go to next question. In a city, 3 English dailies A, B and C are published, and a recent survey of readers indicates the following: A people read 30% people read A paper. Okay. So, probability of the paper A is equal to 30%, that is 3.3. The paper B is read by 20% people. So, probability of B is equal to 0.2. C paper is read by 15%. So, probability of C is 0.15. Okay. 10% is read, 10% people read both A and B. So, probability of A intersection B is equal to 0.10. 8% read both B and C. So, B intersection C, probability of B intersection C is equal to 8%, that is 0.08. Okay. Probability of A intersection C, okay, 4%, that is 0.04. Okay. Now, 2% people read A, B and C. So, probability of A intersection B intersection C is 0.02. Okay. Now, compute the probability that at least one paper among A, B and C is read by a randomly chosen person in the city. So, we need the probability of A union B union C. Okay. And we have done this formula. This is probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of A intersection C plus probability of A intersection B intersection C. Okay. So, P A equal to 0.3, P B equal to 0.2, P C equal to 0.15, A probability of intersection B is 0.10, probability B intersection 0.08, B intersection C, probability of B intersection C is 0.08 minus probability of A intersection C is 0.04 plus probability of A intersection B intersection C is 0.02. Okay. So, let us calculate this. So, 0.30 plus 0.20 is 0.50 plus 0.15, this is 0.65. Okay. And here we have 0.10, 0.08. So, 0.18 and then 0.04 is 0.22 and here we have 0.02. So, how much we get? 0.65 plus 0.02 is 0.67. So, 0.67 minus 0.22 is 0.45. That means 45% people, okay, read at least one of the 3 papers at A, B or C. Okay. Now, find P A XOR B. Okay. P A XOR B, A XOR B means what? Probability of A XOR B is the event that either A or B, but not both will happen. Okay. So, if you take A here and this is B, okay, then this portion is A minus B. A occurs, B cannot occur, and this portion represents B minus A. That is, B can occur, but A cannot occur. Okay. B will occur, but A will not occur. Okay. So, when we say that probability of A XOR B, okay, it means that we need the probability that either A or B occurs, but not both happen together. Okay. Not both will happen. So, XOR means exclusive OR function. This means exclusive OR function. Okay. Now, A XOR B means A minus B, this is A minus B union B minus A. So, probability of A XOR B will be equal to probability of A minus B plus probability of B minus A, because A minus B intersection B minus A is equal to phi. A minus B intersection B minus A is equal to phi. So, probability of A XOR B is equal to P A minus B plus P B minus A. Okay. Now, we know that P A minus P A equal to P A minus B plus P A intersection B, because this is equal to P A minus B plus P A intersection B, because A minus B and A intersection B are mutually exclusive. So, probability of A will be probability of A minus B plus probability of A intersection B. Similarly, B minus A and A intersection B are mutually exclusive. So, P B equal to P B minus A plus P A intersection B. Okay. So, these give you the values of probability of A minus B, which this is equal to probability of A minus probability of A intersection B and probability of B minus A, which is probability of B minus probability of A intersection B. Okay. So, let us put the value of P A minus B and P B minus A. What we will get? P A plus P B minus twice P A intersection B. Okay. So, this is how we get the value of A XOR B. Now, let us consider this problem. The probability that a contractor will get a plumbing contract is 2 by 3. So, let us say A denotes the event that the contractor gets the plumbing contract. Okay. Then probability of A is equal to 2 by 3 and the probability that he will not get an electric contract. So, let us say that B denotes the event that he gets the electric contract. Okay. So, then we are given that P B complement is equal to 5 by 9, okay, where A denotes the event of that the contractor gets plumbing contract. Further, let B denotes the event, where B denotes the event that the contractor gets the electric contract. Okay. So, P B dash is equal to 5 by 9, which implies that P B equal to 4 by 9. P B dash equal to 5 by 9. So, P B equal to 4 by 9. Now, if the probability of getting only one contract, probability of getting only one contract is 4 by 5, what is the probability that he will get both the contracts? So, here we are given the probability of getting only one contract, that is either A or B, but not both. Okay. So, probability of A XOR B is given to us. Probability of A XOR B is 4 by 5. Okay. Now, A XOR B is equal to P A plus P B minus twice P A intersection B. Okay. So, P A XOR B is equal to P A plus P B minus twice P A intersection B. Okay. So, this is 4 by 5 equal to P A equal to 2 by 3, P B equal to 4 by 9 minus 2 P A intersection B. Okay. So, what do we get? 2 P A intersection B is equal to 2 by 3 plus 4 by 9 minus 4 by 5. Okay. So, from here we can get the value of A intersection B. So, this is 395, okay, 395 LCM let us find. So, this is 45, okay. So, we get 15 to the 30, then 5 9 5 ja 45. So, 5 4 ja 20, and then 5 9 are 45, no 9 4 are 36. So, we get 50 minus 36, that is equal to 50 minus 36 is 14 by 45. Okay. So, that is the answer in this case. Okay. Now, let us go to this question. Events A and B are such that P A union B equal to half, P A dash intersection B is 1 by 5, P B dash is 3 by 4. We have to find the probability of A. Okay. So, we are given the probability of P A dash intersection B, means that this is probability of B minus A. Okay. This is equal to 1 by 5. Probability of B dash is equal to 3 by 4, implies that probability of B is 1 by 4. Okay. Now, we need the probability of A. Okay. So, P B minus A, okay, P B minus A is equal to P B minus P A intersection B. Okay. From B, when you subtract A intersection B, you get B minus A. Okay. So, B minus A is 1 by 5. So, this is equal to P B 1 by 4 minus P A intersection B. Okay. So, we get P A intersection B as 1 by 4 minus 1 by 5, means that we have 1 by 20. Okay. Now, P A union B is equal to P A plus P B minus P A intersection B. So, P A union B is half. So, half equal to P A we have to determine, P B we know, this is 1 by 4 and P A intersection B is 1 by 20. So, we get P A equal to 1 by 2 minus 1 by 4 plus 1 by 20, and we have the LCM 20. So, we get 10 here, okay, here 5, here 1. Okay. So, 11 minus 5, so 6 by 20, this means 3 by 10. Okay. So, 3 by 10 we get, and P A intersection B dash is equal to P A minus B, which is equal to P A minus P A intersection B. So, this is 3 by 10, P A is 3 by 10 minus P A intersection B is 1 by 20. So, we get this will be 6 by 20 minus 1 by 20, so 5 by 20. This is 1 by 4. Okay. So, that is how we get the value of P A intersection B dash. With this, I would like to end my lecture. Thank you very much for your attention.